Okay, so so this is actually a summary of the chapter 21. And we are left at a point where we have defined the electric field, right? So the electric field is basically is a field produced by a certain charge distribution. And so we define the electric field at any given point in space. So at that point, there might be a particle or not. So it might be just an empty point as well, but we still define it, right? So we can actually do it for every point in space. So as a result, the electric field is essentially defined at every point. So what we are saying is that if a point particle, right, with charge Q is placed at a point, let's say at a point where field is Q, let's say with field E, then the force on the charges, force on the particle is basically given as Q times the electric field, right? That's the expression in here. How did we come to that point? We have first noticed that the electric force acting on a charge on a particle is proportional to its charge, because the Coulomb's law kind of has a formula where the force is proportional to the product of the charges. So as a result, if I have a point charge at that location with charge Q, then the force applied on that particle is proportional to that quantity. So we just take this quantity out and we just call the rest as the electric field. And this electric field basically depends on the charges of the other particles and their positions and things like that. Okay. So that's basically the electric field concept. We just define it like this. And we just define it through that kind of an expression. In any case, the Coulomb's law can be expressed like that. If I have a point charge Q, then the electric field produced by that point charge at a point with a distance r is given by that expression. So I'm going to write this as a vector expression. So it's equal to 1 over 4 pi epsilon 0 little q divided by r squared times the argument vector. Okay. And then, yeah, the interpretation comes like that. So if I have this point charge in here, right? And another point charge at that location, right? In that case, the force on that, the other charge is basically Q multiplied with that electric field. So therefore, we basically recover the Coulomb's law in here. Okay. So the nice thing about the electric field is that I mean, instead of a point charge, I might have a point charge distribution in here, a complicated charge distribution. So I can compute the electric field for that charge distribution. And in that case, I can compute the force applied on any point charge in here. Okay. In any case, so I'm going to raise this actually. So in here, therefore, we then talk about in a way, the relationship between a particle with charge and the concept of electric field. So there are like these two aspects. We say that a particle with charge produces an electric field. That's the first aspect. And the second aspect is that if there is already an electric field produced somewhere, and there's an electric field in space, and you place a point charge in there is a force applied on it. Okay. So in a way, this is basically some kind of an interaction between something that we call an electric field and particles with charge Q. Okay, so the field concept, the electric field concept is basically first introduced as a mathematical convenience, right? To simplify the solution of some certain problems with a continuous charge distribution, for example, right? As a mathematical convenience. But at some point, some people realize that this field also might have a physical existence as well, right? And this is kind of hard to understand because the physical entities that we interact with is usually better. Like this pen, for example, it is formed from atoms. Well, it's formed from particles and things like that, right? So I basically interact with it in some certain ways, right? I can touch it and I can, I don't know, see it and things like that. Okay? So claim that anything other than matter has some physical existence is kind of difficult because you cannot interact them in the same way, right? So the electric field is something like that. It is something that you cannot touch. It's something that you cannot see, but probably it exists, right? So there are some indications that the electric fields have a physical existence that actually tells us that, well, it is not matter, it's not formed from atoms and things like that, but it's something that exists, right? Basically, the clues are that, so we are going to see this later, we are going to see that the electric field actually has some energy in it. So as a result, to produce an electric field or to modify it, you need energy and you somehow do some work on it. And that energy stays there, and then you can take it back if you want. And there are some situations where if there's an electric and a magnetic field as well together, these fields also carry momentum as well, right? And so as a result, there are some situations where you can perhaps discuss the conservation of momentum by including the fields into the picture as well, right? There are these kind of situations which are kind of early at that stage to discuss about these. But what I need to say is that, first of all, that the electric field is not just a mathematical convenience, but it is something that exists, right? It is something which is physical, right? So as a result, I don't know, I mean, I can perhaps count things that has physical existence. One of them are like particles like electrons and protons and things like that, atoms and things like that. And then in addition to that, we have something called an electric field, all right? So that field is something that's defined everywhere. So it's not just in here, but at every point it is present. So the word field actually implies that it is a quantity that's everywhere. Right? It's a property of, I don't know, it's something that is everywhere, okay? It's not like a particle, so it's unlike a particle actually. I think, I don't know, perhaps the air around us somehow can be considered as some kind of an example, but a quantity which is a field, for example, might be, I mean, if I want to give an example to a quantity which is a field, I can talk about pressure, for example, pressure of the air. So if you just keep in mind that air is everywhere around us, so it's some kind of a medium, but the pressure of the air is a quantity that is defined separately. It has a value separately at every point in space. The pressure is, for example, is an example of a scalar field, right? Electric field, on the other hand, is a vector field. So it is present everywhere, but the quantity itself is a vector quantity, right? So it not only has a magnitude at every point, but it also has a direction as well. So there are some situations where this electric field, for example, changes with time. It's not always constant. And so as a result, we can then talk about the waves that travel on electric field too, right? So in any case, it's a little bit more modern point of view. So the electric fields and the magnetic fields, these are not the only fields. We know that there are other fields as well, especially in modern particle physics, like the Higgs field and things like that, right? So as a result, I mean, this is just the first example of a field, which is a physical entity and which is something that's present everywhere in space. Okay, so I mean, at some point, we just accept this as physically existent being, actually. And what is nice thing about is that I can basically explain the electric force applied between two charges, right? We actually say that the particles with charges actually do not interact with each other. They interact with the electric field. With the electric field. All right? Basically, we have like these two physical entities that are interacting. So one of them is a particle, and the other one is a field. So this interaction has these two aspects. So if there's an interaction, basically, both of them are basically changing their states. So first of all, a charge, for example, modifies the electric field, right? Charge modifies the electric field in space. So that interaction changes the field, basically, changes the behavior of the field, for example. So it just, I mean, that field is somehow modified because that charge basically produces an electric field. There is a second aspect in here. So if there is a field present, but perhaps produced by some other charges, and we have a charge in here placed within that field. So in that case, we say that the field applies a force on particle with charge. All right. So in any case, so as a result, I mean, therefore, we don't have really an interaction between two charges, two charged particles. It's actually some kind of an interaction with a medium, but since they are interacting with the same medium, say they effectively appears like they are interacting with each other. But in reality, the charged particles only interact with the electric field, right? So the idea is there's something like that. So if I have a point charge in here and another point charge in here, what happens is that this point charge is going to produce an electric field. So let me call this as Q1 and Q2, all right? Sorry about that. The notation will be actually much better in that case, right? So in that case, I can say that the basically charge Q1 produces field E1, and so that's the first interaction perhaps. And the second interaction is that the this E1, so the field color is terrible, sorry about that. Field E1 applies a force on charge Q, on charge Q2, let's say, right? So the force on the charge Q2 would be like Q2 multiplied with E1, okay? So in both cases, the field is actually interacting with these two charged particles, but it appears that, I mean, since we don't see the field, it appears like these two charged particles are actually applying forces on each other. So this, in a way, solves, place that basically force mediated by the electric field. Okay. In a way, this solves the action at a distance problem. Action at a distance problem is this problem. It's actually a very old problem that's present in Newton's time. So we say that the Earth, for example, has a gravitational pull on the moon. So it applies a force on the moon, but they're not near to each other, right? They are too far away. So how can an object in here apply a force on a faraway object? So the field explanation is a very good explanation here. Well, it says that, well, this object in here produces a field around itself, and this field somehow, since it's a field, I mean, the change it produced in the field, it just propagates in space to far away places. So it also extends to the place where the moon is. So somehow moon fields the change in the field, and so therefore there's a force applied on the moon. So it's not a direct force applied by this object in here on the moon. It's basically a force which is mediated by some kind of a medium. So for the case of gravitational force, the medium is the space-time. For the electric force, is the electric field. Okay? So we are going to have the same kind of a interpretation for the magnetic force as well. I don't know if you have any questions here. So I'd like to spend too much time to explain this. But I mean, it's an important point of view, all right? So as a result, at this point, I'm going to ask you to accept the electric field as a physical entity. Okay, so charged particles interact with the electric fields. Neutral particles do not interact with them. Only the charged particles interact. So the charge is essentially the coupling constant of that interaction, right? It tells you how strongly your particle interacts with the field, right? And if you have two charged particles, it appears that they apply forces to each other, but they don't. They are basically interacting with the same medium, and somehow it appears that they are interacting, but they really do not. Okay. So, I mean, this is an important point of view. As a result, we are going to use this from this point of, and from that point of, we will just really be talking about the electric fields and not the electric force. So there are some situations where we also need to talk about the force as well, but this time we are going to talk about the force applied by the field, right? So the electric field would be our central object from this point to the middle of the semester, essentially. Okay, so in chapter 21, we have like two topics. One of them is the basically E field produced by a continuous charge distribution. And the second one is the electric dipole concept. Electric dipole. So I'll try to explain them, but I'm not going to solve any problems here, right? So it's just a qualitative explanation. I mean, in both cases, there are some formulas actually. So for this one, I'm going to actually talk about some certain situations, certain kinds of problems which can be solved by using this Coulomb's law approach. In the second chapter, chapter 22, there is actually a different mathematical technique called the Gauss law. Gauss law also is a technique that is used to solve that problem. So we are going to solve the same problems from that point of view later. So it's important that you learn both, because there are some certain problems where we can solve the problem only by one of these. And there are some situations where both of these methods are useful, but one of them is easier than the other one. As a result, it's important that you actually learn about both of them, right? So in any case, for this one, I'm going to start with this. The basic idea is something like that. If we have some kind of a charge distribution in here, the problem is usually like that. There's a point in here, and we would like to find the electric field at that point. Okay, so let's say it like this. Find the electric field at point B. Okay, so what we do is we actually, I mean, this is the natural thing to do. So we just think of this continuous charge distribution as, I mean, we just divide this into small pieces, right? So I did this wrong. So I'm just going to divide some kind of in some certain way, this charge distribution. So this a small piece on the on here is going to be called dq. Sorry about that. I think I'm going to do it like this, right? So this is the continuous object, perhaps. So what I'm going to do is I'm going to just consider a small piece of charge in here, but it's I'm going to call the charge in here is dq. So basically, we need to divide the object, let's say, into small. It's going to be basically infinitesimal pieces. Okay, when I say infinitesimal, I actually mean from the integral point of view. It's a quantity which is so small that at the end I just take the limit where this goes to 0. So in any case, so as a result, all of these infinitesimal quantities I'm going to show with this d symbol. dq is an example, for example. So that's the charge on one of these pieces, right? On a piece. So for that charge, we just think about the distance to the point in question and the electric field produced by that charge. Okay, and this is basically given by the Coulomb's law expression. Right? That's 1/4 pi epsilon 0 dq divided by r squared times the r unit vector. Okay. And then we have to sum this, right? Sum all of them. As a result, the total electric field at the point in question can be expressed as 1/4 pi epsilon 0 and the integral of dq divided by r squared times r hat. Okay, so that's the formula, but unfortunately, this is not a ready to integrate formula. It's just a recipe. A recipe is basically a set of instructions that tells you what you should do, right? It tells you that you have to divide the charge into these small pieces. For each piece, compute the distance to the point in question. For each piece, compute the radial unit vector. And then multiply them and then do some integration and things like that, right? So as a result, I mean, it doesn't mean that, for example, there's a variable q and this dq is the differential of that variable. No, that's not the case. And similarly for this de in here. Right? So that dq in here, that d in here, is just a reminder that this charge on the piece is actually an infinitesimal quantity, and we have to take a limit where this thing goes to 0. Right? It's just a reminder like that. And similarly, that de in here. Right? It's just a reminder that this is extremely small, it's an infinitesimal quantity. But it's not a variable. So somehow you have to use some kind of a variable to convert that integral into something that can be integrated by using calculus. Okay, there are many problems like that. I'm not going to solve any of them. I'm going to just say something more about these. Right? So first of all, this is a recipe. And second of all, since this is a vector expression, I have to do a vector integration. Okay? But it is quite hard to do this with vectors. Instead, people just look at the components of this thing here. So in any case, so we have a radial unit vector in here at that point. This is a vector. It also depends from point on the point in question too. So as a result, I mean, this integral can be decomposed into the x, y, and the z components. So normally what we should do is we have to integrate only a component. So this is the formula in here. I need to write down the x component of the r hat in here and then do the integration. And repeat the same thing for the y component and for the z component as well. And so that's y and that's z. Okay, so it was kind of unnecessary to repeat everything in here, but since I have written down, right? So what's important in here is that I have to look at a component to integrate. We can only integrate. I mean, it is better to integrate scalars. So therefore, for this reason, since this is a vector equation, I have to look at the components, each component, and then do the evaluation for each component separately, right? That's what we must be doing. Okay. That's one of the things that we should keep in mind. And there are some problems where you can actually tell that some of these components are equal to 0, right? So in class, I have solved this problem. This is usually the problem that I solve. So we basically have a rod, thin rod with length L and charge Q distributed uniformly. All right. So it's I don't know, rod like that, and then we have a point at a distance a from one end, and you would like to find electric field in here. Okay. There are many issues in here that perhaps we can discuss, but I mean, that's the problem. I'm not going to solve that problem, but I just want to notice a few things in there. So, for example, to integrate this, we have to choose some kind of a coordinate. Usually for this kind of linear problems, it is the Cartesian coordinate x, which is more suitable. So I'm going to use a yellow x-axis like that. All right, I choose an x-axis like this. So, for example, I mark the left end as the origin and the right end therefore has a coordinate x equals L. So any piece of charge in here can be described as some kind of an interval in here where the left coordinate is x and the right coordinate is x plus dx. Okay. So in any case, the charge in here will be dq and so on. Okay. And as a result, you need to write down this integral in here and find the electric field in here. So we just noticed that, for example, in here, in this particular problem, the y component of the electric field and the z component of the electric field is already 0. I mean, there are some certain reasons for each one. So there are like problems where you use symmetry arguments to show that some certain components are equal to 0. Right? You basically have some idea about the direction of the total electric field produced there because of some symmetry reason. Right? In those cases, you don't have to form these kind of integrals. And I mean, if I already know that Ey is equal to 0, I don't need to form this integral in here. So in this particular case, the reason why Ey is equal to 0 is that this is also equal to 0 because the radial unit vector in that case is always the I unit vector. But in any case, so we only have the x component in here. Okay. So whatever. I mean, I'm not going to, as I said, I'm not going to solve this problem in here, but I'm just going to summarize what I have done in class. Okay, so the first problem that I have solved is this. I mean, please look at this problem. So it kind of introduces the essential ideas. It is simplest because we only have the x component in here, and as a result, you don't have to consider the y and the z components. The second problem is an infinite thin line. Line of charge. So in that case, we have an infinite line of charge. I mean, it is similar to that, but it is infinite. So it's therefore it's extended to infinity. In that case, the total charge would be infinite, but instead we talk about the linear charge density in here. Okay? And we would like to find the electric field at a point at a distance r. Okay. This is also a typical problem. It's also a problem that can also be solved by the Gauss law. But again, it is important to know how to solve this. So in that case, for example, if I choose the x-axis like that and the y-axis like this, in that case, both the x component and the y component are non-zero. The z component is equal to 0. But it turns out that the integral of the x component is equal to 0 as well. So somehow even though I mean, each piece in here produces an electric field at that location with a non-zero x component, their integral is equal to 0. So therefore, something that we don't need to compute. Okay. All right. The next problem that I have solved is a thin ring. And it's something like that. I have a ring of charge with charge Q. There's also a uniform distribution in here, and the radius is R. And we have a point in here. This time we use a Z coordinate in here. I used Z actually for that distance. And we would like to compute the electric field in here. So that's also one of the simplest problems. Okay. In all of these expressions, the word thin means the thin here. Thin means that the thickness is negligible compared to other length scales. So that's how the physicists say. Mathematically, it means that when you see the word thin, it means that you have to take the thickness to be equal to 0, right? So mathematically, we just work with the idealized situation. So instead of a rod, we just think about a line, right? A mathematical line with 0 thickness and a certain length in here. Okay. So here it's an infinite line with 0 thickness again. So this thin ring is actually a circle in that case, mathematically. But physically, we don't have a circle or a line as a shape. Everything is made up of atoms and particles and whatever. They have a size as well. In that case, physically, what we are saying is that the size of the thickness is small, negligible compared to all the other length scales, right? And then we solve this a thin disk. So it's a disk this time, so it also has some kind of a thickness, but that's negligible. In that case, the charge is Q again. So the distance is Z. And we would like to find the electric field at that point. And finally, an infinite sheet of charge. So this problem is also important. Again, it's a problem that can be solved by the Gauss law as well. So instead of a disk, we have a disk with an infinite radius. So this has a radius R. That you can think of this as a disk with a radius infinity. So the sheet is infinite. So it's actually extended in all directions. In any case, so you would like to consider a point in here, which is at a distance Z from the sheet, and you would like to find the electric field at that point. Okay, so in this case, the parameter is the surface charge density of the sheet. Okay, I mean, you have to look at the solutions of these problems in this chapter, in the chapter 21. This basically involves the integration of the Coulomb's law, right? It is important that you look at them, because there are some important mathematical techniques in there and things like that. So for example, in here for the disk problem, we have to divide the disk into small pieces, and there's one best way of doing this, right? We have to divide it into small rings, for example. So just keep this in mind, right? So there are some certain nice mathematical techniques that we need to use. Okay. So as I said, I'm not going to show anything in here. Okay. So as I said, this is one half of chapter 21. The other half is about the dipoles, the dipole concept. And the dipole concept is basically is essentially coming from the molecules, right? There are things like, for example, the water molecule. Right? It basically has an oxygen, and then there are these two hydrogens, and they actually make some bonds in here. So probably that's some kind of a picture of the molecule, right? So there's an oxygen in here and a hydrogen in here, right? In any case, so the total charge of the molecule is 0, but there's actually some kind of a charge distribution in here. So there are some oxygen side is negatively charged, and the hydrogen sides are positively charged, right? So it's a molecule where, although it's charge neutral, there's some kind of a charge distribution inside, right? All the charges do not cancel each other, because positive charges and the negative charges are somehow separated from each other. What this means is that this molecule actually interacts with electric field. Okay, even though its total charge is equal to 0. So as a result, as a particle, it's a particle with 0 charge. So normally it should not interact with the electric field. But since it's made up of smaller charges and these charges are separated, it actually interacts, right? So the dipole concept is actually introduced to actually systematically discuss the interaction of such molecules with the electric fields, right? In a way, this is the next level of, I don't know, quantifying charge distribution. So first of all, a dipole is, usually we just simplify it, right? This is a simple dipole model. Sorry. In the simple model, we just think of this as a point charge with charge minus Q, and another point charge with charge plus Q, which is separated by a distance d. Okay. So just like in a molecule, we are going to assume that that distance is fixed, but its orientation can change. It's like a molecule, right? A molecule can change its orientation, but it doesn't change its shape. I mean, we are assuming that the shape of the molecule doesn't change, right? It just rotates. So, I mean, in reality, of course, the oxygen-hydrogen length, for example, bond length also changes. There are some vibrations and things like that. But let's just ignore this. Think of this as a rigid body. So this dipole is also some kind of a rigid body here. So the charges are separated, but the distance, the relative position, relative distance between them is fixed. So it can rotate, but that distance is not going to change in magnitude. Okay. So this is the simple model. By using this simple model, we actually have a quantity called the electric dipole moment. Electric dipole moment. So it's usually shown by the symbol P. It is simply defined as the charge, this charge Q in here multiplied with the distance. Okay. Here the convention is that the distance is should be defined starting from the negative charge to the positive, ending up at negative positive charge. Sorry. And the way to remember this is that you would like to always go from negative to positive if you are a positive person, right? You may start from negative perhaps, but you should always go to positive. Right? Unfortunately, the chemists actually use the other convention. They start from the positive charge and then draw to the negative charge. Something that you may want to keep in mind, but this is the physicist definition. That's actually much better. There's actually another way of doing this. So suppose that you have some kind of an origin here, and let's say that the negative charge has a position Rn, and the positive charge has a position, let's say Rp, right? So the dipole moment is basically can be defined as the sum of charges multiplied with the positions, right? In that case, what you need to do is you have to multiply the charge of the negative charge with the position of the negative charge, and then add up with the product of the positive charge with the position of the positive charge, right? So in that case, you can see that this formula gives you Rp minus Rn, which is essentially the relative position between these two particles. So that's equal to the D that we have defined over there. So this is going to produce the same expression. Okay. So it's basically a more general definition. All right. And this is why we are using this definition actually. This is why the physicist definition of the dipole moment is best, because this formula is a simplified formula. Okay. If you have more than two charges, like, I don't know, let's say minus 3q charge in here, and a plus q charge in here, and a plus 2q charge in here, I can think of this as like two different ways. I can think of this as two dipoles with dipole moments like that. So first dipole is this dipole with a dipole moment defined like that. It's along that direction, and this together with the this dipole in here, where the negative charge is minus 2q and the positive charge is plus 2q, right? So this has a dipole moment, I don't know, let's say P2 in here like that, right? I don't know if this is understood, right? So, I mean, we have a system where the total charge is 0, but we have more than 2 charges. So in that case, you can consider it as like a dipole combined with another dipole. And in that case, the total dipole moment is given by sum of the dipole moments of these two dipoles, right? You can do it like that, or you can use this formula that I have given over here. So in that case, you are going to have only 3 terms in here, but eventually you are going to compute it. Okay. So there is actually a question in one of the online homeworks that you can solve it like that. Okay, so why do we define it like this? Why do we define the dipole moment like that? Why this particular definition? I mean, why not q squared times d, for example, or things like that? So the answer to that question is this. So it appears that when you describe the interaction between a dipole moment, a dipole with the electric field, it appears that this dipole moment is the coupling constant, right? So in any case, a dipole produces an electric field outside, and it appears that this electric field is proportional to the dipole moments. And the other case, so if I place a dipole inside an external electric field, this external electric field applies some forces on the dipole, and those forces and the torques actually, it also depends on the dipole moment. So none of these interactions depend on Q only or D only, or I don't know. I mean, somehow that interaction depends only on this product of the charge and the separation, right? That's the reason why we define a quantity called the dipole moments. Okay, so there are a few things that I need to describe in the physics of the electric dipole moment. As a result, let's postpone this to tomorrow, right? So tomorrow at Friday, right? Tomorrow is Friday, is the 24th. So let me write it in here. But let's say extra class So let's see, this is March 24, Friday, at 4:40 well, I think I'm going to spend more than 1 hour in that. So we can do it as 2 sessions. So I can then talk about the dipoles, some physics of the electric dipoles. And then after that, I can then describe the Gauss law. Okay, so let's finish it now, because I need to leave now. All right. So if you have any questions, I'll be waiting for your questions.